Hi everyone, today I'll be talking about PIRLNav, pre-training with imitation and fine-tuning for ObjectNav. This work was done with my collaborators at Georgia Tech and FAIR at Meta AI. In this work, we present an approach to combine behavior cloning pre-training on human demonstrations and fine-tuning, which enables effective object goal navigation. In ObjectNav, the agent is tasked with searching for and stopping at an instance of a goal category, for example, a cushion in an unseen environment. The agent is provided with RGPD input and it also has access to GPS with compass for localization. In this paper, we present a simple three-stage training method that uses ObjectNav demonstrations collected from mechanical Turk workers to pre-train a policy using behavior cloning. Next, we fine-tune the policy using RL. To do so, we first pre-train a critic using rollouts from the frozen behavior clone policy. Finally, we fine-tune both critic and policy in an interactive learning phase. Using this three-stage training recipe, we learn a policy that achieves state-of-the-art results on ObjectNav benchmark. Next, I'll talk about the paper in more detail. Prior work has shown imitating a large dataset of human demonstrations using behavior cloning leads to state-of-the-art results on ObjectNav. However, behavior cloning has two primary issues. Policies trained with behavior cloning fail to generalize to out-of-distribution states not seen during training. Second, it is expensive to scale the dataset to improve performance on the task. On the other hand, RL for ObjectNav is trivially scalable once you have access to a simulator, but RL requires careful reward engineering to perform well on the task. One might ask, can't we just combine behavior cloning and RL by pre-training with behavior cloning and fine-tuning using RL to get the best of both worlds? However, RL fine-tuning a behavior clone policy is challenging because behavior cloning pre-training results in the weights of the policy, but RL training requires access to a policy that acts in the environment as well as a critic that estimates how good the states we are in during training. One might ask, why not just randomly initialize a critic during fine-tuning and learn it from scratch? We find naively fine-tuning a policy using randomly initialized critic leads to policy performance dropping significantly early on during training since the critic provides poor value estimates. To tackle these issues, we present PIRLNav, a simple approach to combine behavior cloning pre-training on human demonstrations with RL fine-tuning on ObjectNav. PIRLNav allows us to use less number of human demonstrations for pre-training, saving data collection cost, and enables RL fine-tuning without reward engineering and achieves SOTA results. PIRLNav is a three-stage training method. In the first stage, we pre-train a policy using behavior cloning on human demonstrations. Next, we pre-train a critic by rolling out trajectories using the frozen behavior clone policy. Finally, we use the interactive learning phase where we fine-tune both the policy and critic using experience collected online by the policy. We find naively switching from phase 1 of RL fine-tuning to phase 2 leads to small improvements in policy performance when using a very high LR. To remedy this issue, we use a learning rate decay and warm-up schedule where after the critic pre-training phase, we linearly decay the learning rate for the critic and linearly warm up the learning rate for the policy to a fixed value. Once both of them reach a fixed value, we train the policy till convergence. We find that using this learning rate schedule helps improve performance by a large margin. To support this, we present ablations of our RL fine-tuning regime to quantify importance of each phase in the approach. For our ablations, we use a policy pre-trained on human demonstrations. As initialization, the dataset size we use is 20K human demonstrations for pre-training. First, naively fine-tuning the policy without critic pre-training improves it by just 1.6% on success. Next, with only a critic learning phase, the policy improvement is 3.1%. Next, adding a critic LRDK helps improve policy performance by 2.7% and 1.5% when we use just active warm-up phase. Finally, using both the critic learning phase and LRDK as the PIRLNav approach improves policy performance by 10.2% on success rate. Note this improvement is significant. With just using 20K demonstrations for pre-training and RL fine-tuning using PIRLNav, we already achieve state-of-the-art results on the benchmark. Next, we present our best results on the HM3D ObjectNav challenge using our approach of pre-training using behavior cloning on 77,000 human demonstrations followed by RL fine-tuning for 300 million steps. We achieve 65% success rate on the benchmark, which is a 5% improvement over state-of-the-art results on ObjectNav. Next, we investigate how behavior cloning pre-training and RL fine-tuning scales with number of demonstrations we use for pre-training. For pre-training, we For pre-training using behavior cloning, we see promising scaling behavior with more demonstrations. As we scale the dataset size, the behavior cloning performance keeps improving. Interestingly, we find that as the dataset size increases and we get to high behavior cloning accuracies, the improvements from RL fine-tuning start to diminish. For example, when we use 20K human demonstrations for pre-training followed by RL fine-tuning, we just get a 10.1% improvement post fine-tuning, while when we are using 70K demonstrations, the improvement is just 6.3%. Both of these suggest that by effectively leveraging the trade-off curve between the pre-training dataset size versus the performance gains after fine-tuning, it may be possible to achieve close to SOTA results without large investment in number of demonstrations. Our choice of human demonstrations for pre-training was motivated by results from prior work. We also examined if any other cheaper sources of demonstrations could lead to equally good generalization. Specifically, we considered two other alternatives. The first one is shortest paths that are generated with the help of a map of the environment, where we just plan the shortest path on the top-down map of the environment from a source point where the agent is to a destination point where the object is. Another alternative we use is frontier expert demonstrations. These are generated using a two-stage method where we first explore the environment using a task-agnostic exploration strategy to build a semantic map of the environment. And once the goal object in the map is detected, we use a path planning algorithm on this top-down map to reach the goal using the shortest path. We find that human demonstrations are key to good generalization on ObjectNav. Any other alternative source of demonstrations doesn't lead to equally good performance on ObjectNav. Read our paper for more details on the specific experiment. Now we take a look at the failure modes of our best performing policy. We find our approach has significantly small number of exploration failures and majority of failures are due to annotation issues. Here's an example of early stopping behavior where the agent reaches close enough to the goal but calls stop action right outside the success radius because it cannot see the glass table in front of it. Next, you can see an example of missing annotation. Here the agent successfully locates the goal TV monitor but fails because the annotation for this specific TV monitor instance is missing. Our agent also fails to navigate between floors. In this example, the agent cannot find the bed on the current floor and it needs to navigate to a higher floor to find the bed. Here's an example of exploration failure. Here the agent cannot get out of the living room and just keeps looping in the same area, failing to explore. Finally, you see an example of recognition failure. Here the agent sees the goal object but fails to stop when it reaches close enough to the object. Key takeaways from our work are combining behavior cloning and RL for ObjectNav leads to state-of-the-art results. As we scale behavior cloning pre-training dataset size, improvements from RL fine-tuning start to diminish. Finally, human demonstrations are critical for good generalization on ObjectNav. Thank you for listening.